Hi everyone, welcome back to Math 112. This is Scott. Let's get started. So today we are going to be following up on our investigation of angles and seeing what use we can have for them in terms of finding the trigonometric functions. So this is going to be our first introduction to 6 lifelong friends. Trigonometric functions. A unit circle approach. All right. So first off, let's just discuss our setup. The title of this section is Unit Circle Approach, but actually we'll find it useful to be a little bit more general than that and talk about circles of any radius. The only thing that's really important is that the center be at the origin. So a circle with radius r, so not necessarily just one, is centered at the origin. Okay, so that's our setup. So that's what it looks like. All right. The angle theta in standard position corresponds to the point xy. All right. So what we have here is an angle in standard position. Remember what that means. That means starting over here at the eastern side of the circle, we traverse it in a counterclockwise fashion, the sens trigonometrique. All right, so there's theta, standard position, and what this is saying is the point that is along the outside of the circle here is going to be called x comma y, just so we have things to call them. Okay, now with this setup, we can start to delve into the trigonometric functions. So first off, the sine and the cosine. So the sine. So the way we write it is sin and then whatever the input is. This is a function, and so it takes an input. So usually with functions, you write them like f of x, things like that. Here we do the same thing. We write sine of whatever, and if the argument of the function is in any way some kind of complex expression, we will put parentheses around it, but if we can ever avoid it, we will, because parentheses can be a major hassle if you start getting yourself enveloped in too many of them. So wherever we can, without any danger of confusion, we will omit parentheses, but we will put them if they will help clarify anything. Okay, so sine theta is equal to, now this is the original of the trigonometric functions, and it has a long and storied history. It was first studied by Indian mathematicians, in India that is, and it migrated from there across the world, went backwards along the Spice Trail, or went along the Spice Trail, went through the Arab world, and finally into medieval Europe. but basically the way to think of sine of theta is it is the factor that you would multiply the radius by to get the y. So in other words, it's y divided by the radius. So y is equal to sine of theta times r, and here, so here that means that sine would be y divided by r. So it's y in comparison with the radius. And if r equals 1, then we're talking about a unit circle. Then sine theta is just y. Dividing by 1 never accomplished anything. What does it mean to cut something into one part? It means you haven't done anything. Okay. So sine is to y as cosine, its complementary function, is to x. So cosine theta is equal to x over r. And again, if r equals 1, then we can drop the r nonsense and just write cosine of theta equals x. Alright, so those are the two main principal trigonometric functions, and then from them we can combine them in different ways or twist them around in different ways to get four more. So the tangent. So the way we write it is tan theta, and that's equal to, there are different ways that we can write it depending on what's convenient, and we will freely change them around as needed, but basically it is the ratio y over x, or another way of writing it is, if we divide the top and divide the bottom each by r, then what we'd be talking about is tan theta equals sine theta over cosine theta. Okay, so tangent is y over x, and one of the easiest ways of thinking about it is just think of it as the slope of the ray. It's how much it goes in the y direction divided by how much it goes in the x direction. In other words, rise over run. Okay, so that's the tangent, and those are the first three. Now, for each of these, there are the reciprocal trigonometric functions. And these three functions are each the reciprocal of one of the preceding ones. So there is the secant. So secant, which we write SEC, theta is equal to 1 over cosine theta. So there are two ways of thinking about reciprocals. One of them is to just write it as 1 over the thing. The other way is to think of it, if we're talking about a fraction or a ratio, it would be just switch the top and the bottom of that fraction. So another way of thinking about that is that then that would mean that secant theta is equal to, then that would be r over x instead of x over r. Okay, and then for the cosecant function, there's its complementary, its co-function, as it's often said. So cosecant. This one is the reciprocal of sine. So cosecant theta is equal to 1 over sine theta. Or if we want to put that in terms of of r and x or y, it would be cosecant theta is y over r. Sorry, r over y. Wouldn't be much of a reciprocal if it didn't actually flip it. Okay, so we are 5/6 of the way there. There's just one trigonometric function left, and that is the complementary function to the tangent called the cotangent. So, we write cotangent, COT. Some older books or books from other countries will write it COTAN, and they'll actually write this COSEC, but we by default use the more abbreviated version here. So cotangent theta, and that's equal to, on the one hand, it's 1 over tangent. So it is the reciprocal function for tangent, and it's also the complementary function for tangent. It's just an interesting fact about the symmetries of a circle, that these things tend to come in weird little families like this. Alright, and then if we want to put that in terms of x and y, then we would have x over y instead of y over x. So again, reciprocal can be thought of in one of two ways. You can either make it 1 over something, or if it's a fraction, you can just flip it. Okay, so one of our first tasks here is going to be to evaluate these trigonometric functions for points on circles. So evaluating the 6 trig functions, for points on a circle. Alright, so what this means is they'll give us, in the very first instance of this particular section, they'll give us the coordinates of points on a circle, and it'll be up to us to then spin those out into the 6 trigonometric functions. So, case 1. Case 1. We might be talking about a unit circle. And that's a nice one. Case 2. Arbitrary circle, so not necessarily unit. So any r, but if I have to commit myself to black and white, I'm going to specify that r has to be greater than 1, or greater than 0, I mean. Radius of 0, that's just a point, and why talk about the different points along a point? That doesn't make any sense. And if radius is negative, then that doesn't make any sense at all. That just blows the mind. So for an arbitrary circle with any positive radius, that'll be our case 2. So the tool that we'll use for both of these cases we'll set up and simplify the values for sine theta, cosine theta, tan theta, and cosecant theta, secant theta, and cotangent theta. So we'll set up and simplify the values for these 6, and we'll just basically by default always lay them out in this array. So sine, cosine, tangent, and then to the right of those we can just write all their reciprocals. It's the most systematic way we can write it. So we'll set up and simplify the values for these based on the above formulas. And then what we will do is, if necessary, we will perform a feat of simplification that's known as rationalizing the denominator. Note. We will rationalize any denominators that contain square roots Okay. So square roots, we will not want to have square roots of non-square numbers in the denominators of our overall answers. The way that works is, so for example, let's just say 1 over square root of 3. So this is currently an irrational denominator. Square roots, if they are not perfect squares, produce irrational numbers. And that means that they have infinite decimal expansions that do not settle down into a repeating pattern, which in turn means that we're really talking about dividing 1 by something that has just a continually infinite number of digits. And those of you who remember long division may remember that the numbers that you are dividing by, that's what makes it complicated or easy. And trying to divide by a complicated number with a large number of digits is what makes a division cumbersome for both humans and machines. And so we're doing a little bit of service here for our little electronic friends by giving them their denominators in a rationalized form, so that we don't put them through this. And here's how it works. So the technique. Multiply. The top and bottom of the fraction by the square root in its denominator. Then we should then be able to cancel out the denominator square root. Alright, let's put this into practice and see how it works. So for example, if we had 1 over the square root of 3, which is a thing actually, turns out we can end up producing when we are trying to deal with trigonometric functions. This is a very trigonometric looking expression. Okay, so for example here, say rationalize. So rationalize. All right, so let's say what we have, I guess rationalize the denominator. We never, by the way, rationalize numerators. If you have to have an irrational number somewhere, let it be the numerator, not the denominator. Okay, so start with 1 over square root of 3. Okay, so with this one, what we do is we take our number and we multiply the top of it and the bottom of it by the square root that is in the denominator. So we had 1 over root 3 multiplied by root 3 over root 3. And the reason for doing this is upstairs, there's not much going on, but downstairs, if we look at that, remember, if you're multiplying together things that are each within a square root, you can actually bring the square root out to the outside of them both. And so it'd be square root of 3 times 3. Now 3 times 3, of course, is equal to 9, in other words, a perfect square. And so what that means is what we have here is root 3 over 3. And there's no way of writing this that's any simpler than this, not without making an error. So this is the version of this that would be easiest to compute, whether by hand, if you had the decimal expansion for the square root of 3 at your fingertips, or for a machine to compute. It's very important for machines to be given a form of number that's going to require the fewest of their resources. We live in a limited world. We can't afford to go wasting all of our electrons on trying to divide by things with an enormous number of decimal places. Okay. So that's how that works, and this will become second nature to you after a little while, because we're going to be doing this kind of thing quite often in this class. So just be warned. Okay, so let's see. How about another one? How about so what's another kind of thing that comes up in trig? Let's say we have 2 over square root of 3. Wait, we just did square root of 3. How about 2 over square root of 2. Okay, so this is something that comes up pretty heavily actually. So let's try our luck. Okay, so we start by taking this little fraction, and what we do is we just multiply the top and the bottom each by the same thing. Whenever you're multiplying the top and bottom of a fraction by something, or dividing the top and bottom of a fraction by something, it always has to be the same thing if you don't want to go around altering the value. We're not trying to alter the value. That's what equals means. We're just trying to write it in a different format. Okay, so root 2, root 2. All right, now how does that work? So it's going to be 2 root 2 on the top. Downstairs, again, by the same logic, this is going to be root of 2 times 2, which we can just cut to the chase. That's root 4. And then what that means is we have 2 times root 2 up top, divided by just 2 on the bottom. Now then, those can cancel, and that makes that a 1 and that a 1. And so what we have is actually just a denominator of 1. So that means this ends up equaling just, in fact, the square root of 2. So that might be a little bit of a surprise, but 2 divided by root 2 is actually just root 2. If you really think about it, you can probably figure out why. But enough about that for me. Okay, so now back to the game that we were playing before we took this little detour, and that is the matter of evaluating the trig functions. And we're going to first confine ourselves to case 1, which is unit circles. So, let's start with something like this. Okay, so evaluate the 6 trig functions for the angles represented by the following points on a unit circle. So in other words, r equals 1. Okay, so r equals 1. So that's an important feature of this first dose of these problems, because it becomes a little bit trickier if we're not given if r is not equal to 1 by default. All right. So first case, let's just say, how about this? So we're going to just have a point x comma y, and let's just start with something relatively straightforward to get the ball rolling. So let's go with 0.6 and 0.8. 0.6 comma 0.8. All right. Actually, go ahead and make the 0.8 negative. It's good to have some negatives in here, just so we don't get complacent. Okay. Now, let's remember the sine, cosine, and tangent definitions. So first off, let's just identify the roles that each of these are playing. So that's the x, that's the y. So sine theta is equal to, and also r equals 1. So sine theta is equal to, in this case, just the y. Because r equals 1, it would ordinarily be y over r, but it's just equal to y. So sine theta equals y. Cosine theta, that's equal to just the x. Okay, so far, this is child's play. Nothing too hard. Okay, now how about tan theta? Well, if we look over the definitions of these functions, we can see that tangent of theta can be thought of as y over x, or it can be thought of as sine over cosine, so whatever's most convenient for us. And here, they're the same thing, so there's no reason to go around making hard decisions. Either way, it's going to be negative 0.8 on the top and 0.6 on the bottom. All right, now here, if we wanted to simplify this, we could do so by multiplying the top and bottom by 10, say. So that's one way of simplifying it, and then once we do that, we can see a common factor that they share, and that common factor is in fact 2. So if we divide them each by 2, 4, and 3, and we're going to get negative 4/3. Okay, sine is that, cosine is that, tangent is that. We can evaluate this more, and we can get the decimal if we wish, or we can leave it as it is. So there's that. And now the other three. So cosecant theta. That's equal to the reciprocal of sine, or in other words, the reciprocal of the y, but those are the same thing, because we're still talking about the unit circle. So that's 1 over negative 0.8. So radius over y, or it's 1 over the sine, either way. Okay. So now, if we wanted to think about this, we could again multiply the top and bottom by 10. Just a nice easy thing to get us going here. And then we can simplify that a little bit. So we can see a common factor that they share. Also, a positive divided by a negative is just going to be an overall negative, and we would almost always write the negative in the front of a fraction, unless we had some very good reason not to. Okay, so I'm going to do negative 5/4. Okay. And then, so that's the cosecant. Then the secant is 1 over 0.6, which again, we can just write it, multiply the top and bottom by 10, and then we can see how that's going to reduce a little bit, and we're going to have 5/3. Okay, and we will by default revert to fractions whenever we can do so. I mean, some things are just decimals and there's nothing we can do about it, but whenever we can put it into some kind of a fraction, we would prefer to. And then cotangent theta. So this is equal to the reciprocal of tangent. And the reciprocal of tangent is this fraction turned upside down. So what we can do is just flip the fraction that is the tangent. Or if we wanted, we could write it as 1 over negative 4/3 and then simplify that. But why pretend like we didn't just notice what we noticed? And that's that tangent is a fraction already, so its reciprocal will be 1 over. Don't forget, when you're doing reciprocals, negatives stay negative, positives stay positive. But other than that, it is 1 over if it's convenient to do it that way, or flip the top and the bottom if that's more convenient. Alright, so this was one case. It didn't involve really any rationalizing of denominators, although it did involve some perhaps slightly unfamiliar arithmetic as far as simplification of things, simplification of decimals. But now let's have a taste of some radicals. All right, so let's say that what we have here is something like negative √5/3, comma, let's say negative 2/3. All right. So again, so remember, we have the x, we have the y, and r is already known to us to be 1. That's what all of these examples instantiate, is radius 1. Okay, here we go. So, starting with the easy ones, so the sine and the cosine involve no fuss, no muss. We just, oops, but we can't get too complacent here. So negative 2/3 for the sine, so sine is equal to y. Cosine theta is equal to x, negative √5/3. All right, so those were straightforward. Look at the denominators, they're nice and rational, no square roots or anything, so that's fine. Now, when we get to the tangent, let's remember we can write that as sine theta over cosine theta. So what is that? That's negative 2/3 all over negative √5/3. Now, how you proceed from this is a matter a little bit of taste. You can write it as a multiplication by the reciprocal. That's a common and correct way of simplifying this. Another common thing you might do is just multiply the top and bottom by 3. In other words, 3 over 1. So as to cancel the denominator. You cut it into thirds, while then tripling it. That should solve that matter. So then those will cancel, and you'll have negative 2. And those will cancel, and you'll have negative root 5. Now, that's all well and good, except 2 things. Number 1, an easy thing to resolve. We have a negative and a negative, so they'll cancel each other out from the top and the bottom. And number 2, this one is less easy. The denominator is not currently rational. Square root of 5 is not a rational number. So, here we go. What we can do with this is we can multiply the top and the bottom by root 5. This is how we rationalize the denominator. Okay, well, let's see how this plays out. This is 2 times root 5 divided by root 25. Now that is the point of multiplying by what we multiplied by right here. You produce something in the denominator that is a perfect square, so then it will simplify nicely. So we have 2 root 5. Downstairs we'll just have 5. And this is about the best way we can write this without getting anything wrong. So notice it became positive because it was negative over a negative. And notice that when the dust had settled and we had finished our simplification, the root 5 was still there. It was just in the top. What was not still there was any mention of those 3's. So dividing by 3 basically cancel each other out. Okay. Now, let's go with the cosecant. So the cosecant is the reciprocal of the sine. So it's nice and easy because we see the sine right to our left here, and we can just reciprocate it by taking what was on top and what was on bottom and giving them the old switcheroo. And this is still okay. It does not have an irrational denominator, so we can move on with clear consciences. Alright, now the secant. So again, we have a fraction that we're looking at for this cosine there, so we just flip it over. Now we flip it over, and we think we're done, but then we look at it again and we realize, oh, nope, not yet. Not yet. So how do we get this up to code? We multiply the top and the bottom by that radical part of the denominator. And then what's that going to leave us with? Negative 3 root 5 over root 25. In other words, negative 3 root 5 over 5. So this time it's the 2's that disappeared, not the 3's. Interesting, but whatever. Oh, sorry. No, I take it back. Take it back. Observation withdrawn. Okay, now cotangent theta. Cotangent theta. So this is the reciprocal of tangent. So let's just take the tangent as we found it before and flip it up. Flip it upside down. So 5 on the top, 2 root 5 on the bottom. Okay, so once again, we have an irrational factor in the denominator. So we can multiply the top and bottom by whatever we want, as long as it matches the top and the bottom. And we are only concerned about the square root of 5 part of this, so that's the only part that we will actually multiply by. And so root 5 times root 5 is what we have down there. And what's that going to make? 5 root 5 2 root 25 And that, of course, is going to be 5 root 5 over 2 times 5. Now, 2 times 5, it's not too hard to evaluate, but why even do that? I can see that there is a factor of just a spare 5 over there and down there, so those will cancel each other, and that leaves us with root 5 over 2. Okay, so this is what happens if we are in case 1 and we know that it is a unit circle. Case 2. So case 2. So this was all case 1. All right, case 2. What if it is not necessarily a unit circle? So note, if a circle is not known to be a unit circle, we must start by finding its radius. Alright, well if we want to do this, we're going to need a little bit more of a tool. So let's take a look again at the situation here. So the situation was, we have a circle. It's not a unit circle, it's just a circle. It's got some radius, which we wish we knew. And it's got x and y just over here. Well, if we know the x and the y, and we want the r, how can we get them? Well, take a look at that little thing right there. So, if we were to go around dropping an altitude, as it's called, like drawing that line right there, then what we would be producing is, in fact, a right triangle. And this is a right triangle whose side over here is the y-coordinate. The length of that side is the y-coordinate, and the length of the side down here is the x-coordinate. So, then the tool that we can use here is one of the first great, like truly great results discovered in the science of geometry, and that's the Pythagorean Theorem. So if we have a right triangle with legs A, B, and hypotenuse C, then, as you probably know, c squared equals a squared plus b squared. So this is a famous result. It is super useful in all kinds of contexts, and here it's just what the doctor ordered. We have exactly this sort of a situation. We have a right triangle whose two legs we know and whose hypotenuse we do not know, and so we will go ahead and translate this into that. So then r squared is equal to x squared plus y squared. So this is a nice famous little relationship, and it's very, very, very useful in not only this context, but others as well. So burn that one into your minds, folks. This one is it's coming back. Okay. So we can use this to find r. Okay, let's try this out. So as an example, so use this to find r, and then we'll say, and then apply the definitions. So here now, sine theta is y over r, cosine theta is x over r, tangent theta is equal to still y over x, cosecant is equal to r over y, secant is equal to, oops, rewrite the thetas, secant theta is equal to r over x, and cotangent theta is equal to x over y. Just take each of those fractions over there, turn them upside down. All right, let's give this a try. So first off, let's just try this with some suspiciously nice numbers, and then we'll let the numbers get unruly. So example, find the 6 trigonometric functions for the following points on circles centered at the origin. In standard position. So we're talking about an angle on a circle with a radius that could be whatever. All right. Let's say the first one, how about 5, -12. So this is going to be one where where everything's going to work out suspiciously nicely at first, and then we'll get one where things work out less nicely. Okay, so 5, -12. All right, so this is of course the x, and this is of course the y. As for the r, that's for us to determine. So r. So r squared is equal to x squared plus y squared. That's what the wisdom of Pythagoras teaches us. And now let's just see what that means. So r squared is equal to 25 plus, so when you square a negative, it doesn't stay negative, it becomes positive. So this is just going to be positive 144. And you add those up, it becomes 169. And if you take the square root of 169, you will actually find that it is, in fact, okay, so we're solving for r, so we take the square root. We don't worry about the negative branch. We are not concerned with negative values for the radius. And it just so happens that this one happens to be a perfect square. It happens to be 13. If you see a number, always at least punch it into a calculator to make sure it's not a perfect square. Before you go around writing things like square root of 69 or square root of 25, always make sure that 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 you recognize if it's a perfect square or not. All right, now that gives us what we need. So sine theta. So sine theta is y over x. So that's going to be negative 12 over 13. Cosine theta. Sorry, y over r. Y over r. I think I said y over x just now, but I meant y over r. So cosine is x over r. So 5 over 13. Tangent is equal to sine over cosine or y over x, whatever is the most convenient. So we'll just go negative 12 over 5. That seems like the most convenient form. Rather than setting up some big fraction that needs to be simplified, we'll go straight to this one. Okay, now cosecant theta. So these are once again just the reciprocals of the ones that we just found. So cosecant, secant, and cotangent. Take our previous results and turn them upside down. So the reciprocal of 12/13 is 13/12, and negatives stay negative, positives stay positive. So it's negative 13 over 12. This one is 13 over 5, and this one is 5 over 12. Sorry, negative 5 over 12. So whenever we have a negative, you can write it more or less associated with the numerator, or you can put it in front of the entire fraction, but it's very uncommon to write the negative actually in the denominator. Okay, so that's going to be our first one, and now one that maybe will look easier, but will turn out to be harder. So next one, how about 1 comma negative 2? That looks nice and easy. Well, too bad, it's not. So, I guess make the 1 negative as well. I just want to have like a nice healthy mixture of negatives and positives. All right. So once again, this is going to be our x, this is going to be our y. As for our r, that's for us to find out. So r squared is equal to negative 1 squared plus negative 2 squared. So r squared is negative 1 squared plus negative 2 squared. Just remember to be careful here with these negatives and these squares. These are all squares that contain in them negative numbers, so therefore the square will cancel the negative. And that's going to be a 1, and this one's going to be a 5, or 4 I mean, adding up to 5 is what my mind left 2. So r squared equals 5, which means that r equals the square root of 5. Well, so be it. Now, you may be getting a little bit of deja vu from the previous bout of examples, and the reason for that is that this is how you get numbers like what we saw in that first series of examples. So let's get to work. So sine theta. Sine theta is equal to y over r, so negative 2 over root 5. Well, that was easy to write down, but now we realize, we're going to have to rationalize. So we do. So you multiply by the top and the bottom by root 5, and that's negative 2 root 5 over square root of 25, which then just becomes negative 2 root 5 over 5. Okay, so be it. Cosine theta. Well, x over r. would be -1 over root 5. Well, here we go again. Root 5, root 5. And once again, what we end up with here is very similar to what we ended up with just a second ago. There are lots of patterns in this, and if you get a lot of experience at it, you might get pretty quick at these. So it's over root 25, just as it was before. So in other words, it's equal to negative root 5 over 5. Okay. Tan theta. We can write that however we want, and the most convenient way will be with the y and the x. So -2 over -1. That almost works. Just cancel the negatives and then realize, oh, that's really just 2. Dividing by 1, once again, is not accomplishing much. Now, here comes a part that looks pretty uncomfortable. We have to find the cosecant, the secant, and the cotangent. One of those, only the cotangent, is easy here because we're supposed to turn these upside down, and we can see we're going to have to rationalize that, and it's going to be a whole thing. Now, if we want to be clever, we can take what we got as our unrationalized version of the sign, and if it's more convenient for us to use that, we simply can. So it's going to be negative root 5 over 2. You can go through the motions of turning this upside down and rationalizing the denominator and seeing what you get, but I have a prediction. The prediction is that you will get the reciprocal of the original version of the sign. So remember, at first we wrote that down, we were all proud of ourselves, then we realized it wasn't rationalized, and so we went through that business. But in doing that, we did not change the value of the answer, so if it was right before it was still right, it just wasn't written the way we wanted. So we can just reciprocate that. And by the same token, we can do the same thing with the cosine. So root 5 over 1 instead of 1 over root 5, but then that doesn't need to be written like that. Dividing by 1, as I said, not doing much. Okay, now the last one, cotangent theta. So take the reciprocal of the tangent, and that's going to be 1 over 2 instead of 2 over 1. So the reciprocal of 2 is a half. Alright, so there's sometimes things you can do here, such as this, to save yourself a little bit of the grunt work when you're out in the field. Alright, so now let's discuss the evaluation of the trig functions on calculators. So when we are evaluating trig functions on calculators, we need to be mindful of a couple of things. So note. To evaluate trigonometric functions, on calculators, be careful that the calculator mode i.e. degrees versus radians, matches your angle. Also, most calculators don't have any of the fancier trig functions. They usually just have the sine, cosine, and tangent, at least on the face of them. Maybe you can root around in a catalog or something to find the other ones. But if that's your situation, you can just evaluate the more exotic functions in terms of the easier ones. You can use the sine, cosine, and tangent values to evaluate cosecant, secant, and cotangent. Alright, so let's see how this could work. So just as an example, something quick and easy just to make sure we are on the same page. So you evaluate with a calculator. Let's just say sine of 25 degrees. Cosine of pi over, say pi over 5. And since it doesn't say degrees, that means it's by default radians. Let's say tangent of 1. And again, if it's supposed to be degrees, there should be a degree symbol. Let's say cosecant of 10 degrees. Let's say here we want secant of, let's say, pi over 12, and then lastly cotangent of 81 degrees. All right, so I'm going to do these all with just this little calculator. You can use any kind of calculator that is a scientific calculator and has these scientific functions on them, and just whatever you do, just make sure your method or the mode matches what you want it to be. Okay, so just clear away all this. And for this calculator, you can see right there, it says down in the bottom right corner whether it's in degrees, radians, or what have you. So this calculator actually has right here the button DRG. If you see that button on your calculator, then that will be the button that lets you change between degrees and radians. And if you want to know GRD, that's gradients. It's a different thing. It's related to degrees. All right. So we want degrees or radians, as the case may be. And let's say I want the degrees for that first one. So sine of 25. If you have it in degree mode, you don't need to go in and enter the little degree symbol. And that's what I get. Point 0.42 And I'll just round, like so. Alright, now let's say I want the cosine of pi over 5. Now pi over 5 is in radians, so there we have it. And looks like it is 0.809. Okay. Tangent of 1. Oh, wait a minute, make sure radians or degrees. It looks like it's in radians at the moment, so that's good enough for me. So tangent tangent of 1. 1.557. In the questions that you'll have in your homework, it will tell you how it wants you to round it. So what precision? Okay, cosecant of 10 degrees. You can look all over this calculator and you're not going to find a cosecant button. However, it does have a sine button. Don't be fooled, by the way. This is not cosecant, even though it looks like it might be. You know that maybe a -1 power represents a reciprocal, so you think maybe this is the cosecant, but actually it's not. That's the inverse function for sine. It's a different matter. So, okay, what do we want? We want degrees here, and we don't have a cosecant, but we do have a sine. So what I can just do is 1 divided by the sine. And looks like we have 5.759 if I round. Similarly here, if I want to do this secant, I'll go first to radians to make sure that it is it's in the form that I want. And then instead of sine, it's a cosine, and it's pi over 12. 1.035. Now for tangent, or for cotangent, I'll just do the same again. Change to my suitable angle system here, and go tangent 81. And I get 0.158. All right, so that's what you have to do with a calculator. And again, don't be fooled. The buttons that you will find on calculators that have little -1s up in the superscript, those are not the reciprocal functions. Those are actually the inverse functions. The arc sine, the arc cosine, and the arc tangent, which are all of the inverse functions for sine, cosine, and tangent. So don't be fooled. Those are false friends. -1s here mean inverse function, not reciprocal. Okay. So that's how we can do it with a with a calculator. It's pretty easy. But we can actually, for some of the better known angles, we can actually figure out all 6 of the trigonometric functions exactly by hand. So evaluating the trig functions exactly for special angles. All right, so we are going to start by just looking in quadrant 1, because circles are very symmetrical, and so whatever we see going on over there, we can expect to have similar things just just flipped around in all of the other quadrants. All right, so the special angles. So let's just start quadrant 1 of the unit circle. So this is unit circle, quadrant 1. All right, so the special angles that we will be investigating here will be the angles down here, like 0 or 0 degrees. So it's 0 whether you talk radians or degrees, it comes out the same. Here, which is pi over 2, you'll remember, in radians, or it's 90 degrees in the degree system. We've got the halfway mark between them, which is 45 degrees, or pi over 4. And then we've got a couple other of the important angles here. 30 degrees, which is pi over 6, or 60 degrees, which is pi over 3. So these are the special angles that we'll be focusing our attention on for the next few minutes. So our goal is going to be to make a table of values that cover all of these cases. All right. Alright, so let's say here we've got theta. Let's go cosine theta, and then sine theta. And let's just do it first in degrees, because degrees are still, I think, much more familiar to everyone than radians are. So let's just start with degrees. So the familiar values here are going to be 0 degrees, 30 degrees, 45 degrees, 60 degrees, and finally 90 degrees. So a couple of these we can really just see off the bat with our naked eye. So namely the 0 and the 90. So we can tell that this point right here is 1, 0, which means the cosine will be 1 and the sine will be 0. Conversely, that one up there is exactly reverse. So that's 0 for the x value and 1 for the sine. Okay. We are 2/5 of the way there. Alright, but how are we going to find the rest of these? So what it's going to take is a little delving into the world of formulas. Sorry, of triangles. So let's look at it. So let's start with 45 degree. So if we think about a 45 degree angle, what would that actually mean? So we'd be talking about the place on the unit circle that has a 45 degree angle there, but it would also then have a 45 degree angle here. So this is an isosceles triangle, a triangle that has two copies of the same angle. All right, now if we had down here the x, and over here the y, and over here the r, which equals 1 because it's a unit circle. Then we can figure out some relationships here. Namely, this is the same as this, so this is the same as that. This is the point that's right halfway into the circle there, and so the x value and the y value will happen to be the exact same. So are equal. For theta equals 45 degrees. It's an isosceles triangle, which means that the sides have to be equal if the angles are. All right, well, the Pythagorean Theorem always told us that r squared equals x squared plus y squared. But here we can actually do some work here. So r squared is just 1 squared. X squared and y squared are the same, so I can just say x squared plus x squared. So in other words, 1 equals 2x squared. But what's that mean? What that means is x squared equals 1/2, which means x equals the square root of 1/2, which we would very frequently write. So writing it this way is not the worst thing in the world, but the usual way this would be written would be what you get when you simplify it, like so. So you can break it up into the square root of the numerator and the denominator, and the square root of 1 is just 1, the square root of 2 is the square root of 2, and then this needs to be rationalized. So here we go. Multiply by root 2 on the top and on the bottom. And so what we get is that x equals root 2 over the square root of 4. In other words, root 2 over 2. And y equals x, so y also equals root 2 over 2. All right. Well, I guess that answers that. So since this is a unit circle we're talking about here, the x and the y are the cosine and the sine. So x is equal to root 2 over 2, and y is equal to root 2 over 2 as well. Okay, so there we go. We've got an exact value. Now, it's an exact value. It doesn't mean necessarily that you can actually see its value very well. It's the square root of 2 over 2, which, by the way, for the record, is about 0.7, is the approximate value of that number. But let's continue. We still have 2 more to find. 30 degrees and 60 degrees. Let's think about this. 30 degrees and 60 degrees, those are complementary angles. They could be the angles that form the 2 angles that in a right triangle. So let's just think about that right triangle, what it would look like. So we'd have here say something like this. 30 degrees, 60 degrees. And let's just say y and x, as usual. Okay, and that one's 1. Now let's think about this. Can we make any kind of heads or tails of this? We want to try and maybe use a Pythagorean theorem, something like that. But unfortunately, we have 2 unknowns, and the Pythagorean theorem works best if we can fill in all but one of the blanks. So now let's just think about it for a while, and suppose we meditate on it for a long time. and we get frustrated, and we take a walk, and we go to the lake, and we think about it there. And while we're looking at it, looking at the lake and thinking about the problem, we realize that if we just saw the reflection of this triangle in a lake, then that would be 60 degrees, that would be 30 degrees, and what we would actually be looking at then would be an equilateral triangle. So this becomes an equilateral triangle. And equilateral, equal side. So what that means? Okay, well if those are equal sides, and that means that y is actually the same as that side, or y plus y. So if y plus y equals 1, then that means y equals 1/2. Interesting. But r squared still equals x squared plus y squared, which then here would be mystery x squared still, plus 1/2 squared. Which means that r squared would equal x squared plus 1/4. But wait, r still is known to us. This is still on the unit circle. So that's going to be 1. And so what we have is 1 equals x squared plus 1/4. Subtract 1/4 from both sides. That's 3/4 equals x squared. Take the square root of both sides, and that gives us x equals the square root of 3/4, which we can break up into square root of 3, square root of 4, which is 3 square root of 3 all over 2. So that is the so that's the x value and the y value here for this triangle, for the 30-degree angle. But wait, so 30 degrees here, so for cosine it was root 3 over 2, and for sine it was 1/2. But wait, if we were interested in a 60-degree angle, we could just take the paper, turn it on its side like that, and we would be looking at a 60-degree angle instead. So here it's the same thing, but just reversed. Because these are complementary angles, which means that together they could be swapped around, and you would just get the other right triangle where the two legs got reversed. Okay. So here we have it. We have our table of values. So we have, for the cosine, starts off at 1, so that's the biggest it'll ever be on a unit circle. And then it goes to the next biggest, then it goes to the middle one, then it goes to the smallest value, and then it goes, well, the smallest positive value, and then it goes down to 0. And sine goes in the exact opposite order. And if you look at these, if you stare at them, if you meditate on them, you'll see actually that they have quite a bit of pattern to them. So 3, 2, 1, 1, 2, 3, 0, 1, 2, 3. And in fact, if you think about this as being square root of 4 over 2, we really have even more pattern to it. But meditate on these values for a while, because you're going to need them. You're going to need to know these values backwards and forwards, and in fact, we're going to need to use these values to find other trig functions at other angles. Okay, so that's our table of values. Now, using these. So, we can evaluate all 6 trig functions by using these values. Furthermore, we can evaluate them at angles in other quadrants by comparing their x and y values with suitable values in quadrant 1. Alright, so enough talk. Let's try this. So, for example, evaluate all 6 trig functions for the following. And here's a hint for an approach here. So hint, start by plotting the angle in its rough place in standard position, and that'll help you figure out what the x and the y have to be. So that'll just be a way to get ourselves rolling on this. All right. Note. Some values may be undefined. All right. So here we go. All right. To begin with, let's just start with something relatively minor, namely one that actually is in quadrant 1, just to get us started. So let's say theta equals pi over 3. So this, we've already just covered actually what the sine and cosine would be. Just remember this, so pi over 3, that's 60 degrees, so it's up here. Now if it's up there, that means it's got a big y value and a small x value. So, and they're both positive. So small positive x, that means 1/2, and big positive y, That means root 3 over 2. Okay, so those are the x and the y. And then that means sine theta is root 3 over 2. Cosine theta is 1/2, just as our table said. All right, then tangent theta is equal to y over x. So that's root 3 over 2 divided by 1/2. And the easiest way to deal with that would be you just multiply the top and bottom each by 2 to cancel their denominators. And that's going to give you root 3 over 1. In other words, just root 3. Cosecant theta will be this, just the reciprocal of the sine, so it's going to be 2 over root 3, which, no good. So we multiply by root 3 over root 3, 2 root 3 over root 9, 2 root 3 over 3. So be it. Secant theta. The reciprocal of cosine. That's just going to be a 2 over 1, or just a 2. Cotangent theta is the reciprocal of tangent, which is going to be 1 over root 3. Oops. But that needs to be dealt with, so we multiply top and bottom by root 3, and we've got now root 3 over root 9. In other words, root 3 over 3. Okay. There's that. Now let's try an angle that is not in quadrant 1. B. Let's go with theta equals 225 degrees. So theta equals 225 degrees. All right, so first off, where is that? So that's 180 plus an extra 45. All right, so that means we're talking about it right here, right in the middle there. Now that is a mirror image of the point up here that we're more familiar with. So right there, that's the 45-degree angle, which we know is root 2 over 2 and root 2 over 2 for its cosine and sine. So this one down here has to be those same values but negative. There is just the exact same point but in a different quadrant. And what different quadrants mean is that the x and the y values they have different signs. They're different positive or negative values. Here we're in quadrant 3, which is where both the x and the y coordinates will be negative, and so we get a value negative root 2 over 2, negative root 2 over 2. And so here we go. So sine of theta. Well, we already said it's negative root 2 over 2, as is cosine theta. Tan theta is sine over cosine. Which actually, they just cancel each other and just make 1, which makes sense if you think of tangent as y over x. When y and x are the same, you'll just have 1. The tangent, as I said before, can be interpreted as the slope, and the ray here has slope 1. Alright. Cosecant theta, negative 2 over root 2. So we just turn the sign upside down. But that's not yet right. So we multiply by root 2 over root 2. See what we get. So it's going to be negative 2 root 2 over root 4, which is equal to negative 2 root 2 over 2. Let those cancel, and you just get negative root 2. Okay. Well, we went through all that for the cosecant, but for the secant, it would be just doing the same calculation again, and so we'll get the same answer again. So I'll cut to the chase there. Oops, as for the cotangent, we'll get the reciprocal of 1, which is 1. So what we've got here are this is for one of the 45-degree family of values, and it was in quadrant 3 instead of being in quadrant 1. All right, let's take theta equals negative pi over 2. So again, we just got to think about where to find this on the unit circle. Well, we're supposed to go counterclockwise, but if it's negative, then I guess that means we go clockwise. So that's starting here and goes 90 degrees down to there. All right, well, if that is where we're sitting, then let's look at the coordinates. So I can see that the x-coordinate is 0, and I can see that the y-coordinate is negative 1. All right, so then, what's that going to mean as far as the values go? Well, sine theta is the y value, so that's negative 1. Cosine theta is the x value, and so that's 0. Tan theta is equal to y over x, and negative 1 divided by 0 is undefined. You can't divide by 0. Okay. Cosecant is the reciprocal of negative 1, which is negative 1. Secant theta is the reciprocal of 0, which is 1 over 0, which is undefined. Okay, and then cotangent theta is well, I would say it's the reciprocal of tangent, but tangent wasn't defined, so it's hard to, so you can't really say reciprocal of something that didn't even exist. But the cosine becomes the sine becomes the cosine, the x becomes the y becomes the x, and we've now got 0 over negative 1, which actually is defined. You can have 0 on the top of a division, just not on the bottom. So that's how that one goes. Let's see, what else do we want to have here? How about D? Theta equals 240 degrees. Oops. So let's try to figure out where it is, and then try to figure out what we can relate it to in quadrant 1, which is where we are more familiar. So 240, so that's the same as 270 minus 30. So that puts us down here. 30 degrees off of the South Pole, which then puts us up here as our comparison. Well, if our comparison point is the 60-degree angle up there, then what that means is that our x was 1/2 and our y was root 3 over 2. So that means down here we're going to be in the same situation, just negative. negative 1/2 negative root 3 over 2. So it's got the same x values and same y values as the point in quadrant 1, just both negative. Okay. Well, this is actually rather similar to the values that we had in A, so we can freely borrow our old work here, look it over, and try to find things of use. So let's start with sine theta. So sine theta was equal to, actually we did these exactly, except now they're negative. So negative root 3 over 2. Cosine theta is equal to negative 1/2 tan theta. Before it was root 3 over 2 over 1/2. Here it's negative over negative, which is just going to be the same thing. So this is equal to just root 3. Cosecant theta. So we can compare this with part A. So cosecant theta, that's equal to 1 over the sine, so it'd be negative 2 over root 3, and then in turn that's going to be negative, and we can just cut to the same chase that we cut to before, or that we got before. Negative 2 root 3 over 3, and here again we had 1/2 before, now it's negative 1/2, so secant was 2, now it'll be negative 2. And cotangent theta is equal to, again, root 3 over 3. The values are all going to be the same except pairs of negative on the top and bottom that'll cancel each other out. So this is how this general procedure goes. You just locate the angle first off on the unit circle, and once you have done that, then you can use that to actually evaluate the or to find the comparison value from quadrant 1 that it's most similar to, and then you can use the sines and cosines to get all of the other trigonometric functions. All right, now let's do something a little trickier. So more advanced calculations. We can combine these known exact values and use algebra to simplify. So an example of a problem along this sort would be the following. Find the exact value. And by the way, the word exact here is code for don't use a calculator. Calculators give you decimal approximations of things, but they can't give you exact answers. They can only give you answers that have as many decimal places as the calculator is programmed to give you. Alright, so let's say we wanted something like this. Maybe sine 30 degrees minus cosine 45 degrees. So here, just starting easy, we've got degrees, just sine of something minus cosine of something else. Now the key is just evaluate it piece by piece and then see what you get. Alright, so sine 30, that equals, and again, no harm. No harm in just drawing yourself a quick little orientation unit circle and just ask yourself, is this about the x or about the y? And it's about the y. This is a low y, and that means 1/2. Cosine 45 degrees. So that one was the halfway mark, which is root 2 over 2. Okay. So these are our two pieces of scratch work. Then that means that what we are looking for, sine 30 minus cosine 45, is 1/2 minus root 2 over 2. And since these are fractions with common denominators already, we can actually just combine the two numerators and write it like so. So that's how that one would go. Now let's see, how about something like this? Tangent of 45 cosine of 30. Alright, well again, we need to figure out the pieces before we can find the overall result. So tangent 45 degrees. Well, the x over the y, or sorry, the y over the x I should say, but it doesn't matter because here they're the same. The tangent is always the slope of the ray, and that's equal to 1. Cosine 30 degrees. Now that is again this point right down here, and that has a big X, and that's what we're looking for here, and big means root 3 over 2. So this is the way I think about it. I always think big, little, or small, positive or negative. So big means root 3 over 2, middle means root 2 over 2, and small means just 1/2. And if it's 0 or 1, those are pretty clear, so I don't worry about those. Alright, and so then it's just this times that. Well, if there's ever a number I didn't mind multiplying by, even an hour and a half into a lecture, it's 1. So there's that one. Alright. Let's see. How about one more? So let's go with secant. I don't want to do this. I'm going to do 2 secant pi over 4 plus 4 cotangent pi over 3. Alright, let's think about this. So pi over 4 and pi over 3. Those are the angles. So let's just start with what's easy and just plot those. So pi over 4, that's halfway to pi over 2, so that's putting us at the 45 degree mark. Pi over 3, that's a bigger fraction since its denominator is smaller, so that's over here. Alright, now let's just think about these 2 points. It's root 2 over 2, root 2 over 2. This one looks like the x value is smaller, so it's 1/2, root 3 over 2. Okay, so then secant pi over 4. Well, it's 1 over the cosine, So in other words, 1 over root 2 over 2. Which is equal to 2 divided by root 2, which needs to be rationalized, which gives us 2 root 2 over root 4. In other words, 2 root 2 over 2, and those cancel, and it gives us just root 2. Okay, so good. Now how about cotangent pi over 3? So cotangent pi over 3. So that's equal to the x over the y, and so that's going to be 1/2 over root 3 over 2. And I multiply by 2 and by 2, and that gives me 1 over root 3. And I guess we need to rationalize that one too, so here we go. So root 3 over root 9 is equal to root 3 over 3. Alright, so then, the overall thing that we're looking for, 2 secant pi over 4 plus 4 cotangent pi over 3. That then comes down to saying 2 times the square root of 2 plus 4 times square root of 3 over 3. Alright, so then if we want to try to combine those, 2 root 2, the way that would usually be written, 4 root 3 over 3, and there's not really much that we can do in the way of much more simplification on this, so we won't worry about it too much. Alright. If there were things that were alike, if they had common denominators, we'd combine them. If they even had common radicals, we might combine those. But this is the best amount of simplification we can do, according to the rules that we know for combining different radical expressions. All right. Well, that's the kind of thing that we can now do. The important thing to remember here, once again, to recap. So quadrant 1, recap. This is the most important takeaway from this section. The thing above all, it's important to know, and that would be the coordinates of the key points, the points at the designated important angles in quadrant 1. So here at pi over 2, the coordinates here are 0 for x, 1 for y. That's not so hard. Down here at 0, the coordinates are 1 for x, 0 for y. That's not so hard either. Let's see, at the halfway mark, halfway down the circle, we get, so that's pi over 4, and that's root 2 over 2, and root 2 over 2. At the pi over 6, just think in terms of the x and the y. Is the x big or small? It's big, so that means we're going to have root 3 over 2. And is the y big or small? And that means it's going to be 1/2. And then up here, it's pi over 3, and it's just going to be a small x and a big y. So quadrant 1 recap. So meditate on this, think about it, find patterns in it, find the meaning of it, and you'll be able to find the various trigonometric functions at angles even outside this quadrant. Okay, well, that's going to do it for this section. Thank you for joining me for this episode of Math 112. I'll see you next time. Bye.